Hi, we're going to get going with talking about what the book calls lists and most people call linked lists. But this is another way, another data structure that you can use here. So a list is a collection of items where each item holds a relative position with respect to the others. More specifically, we'll refer to this type of list as an unordered list. We can consider the list as having a first item, a second item, a third item, and so on. We can also refer to the beginning of the list, the first item, as the end of the list, the last item. For simplicity, we will assume that lists cannot contain duplicate items. Okay, so here's an example. We have integers 54, 26, 93, 17, 77, and 31. Might represent a simple, unordered list of exam scores. So note we have rewritten them as a common delimited values. Common way of showing the list structure. Of course, Python would show this list as this with the brackets around it. Okay. So here's the different methods that we're going to be needing for this. We have a list, it creates a new list that is empty. Add, which adds a new item to the list. Remove, removes the item from the list. Search, searches for the item in the list. Is empty, tests to see whether the list is empty. Size, returns the number of items in the list. Append, adds a new item to the end of the list, making it the last item in the collection. Index, returns the position of item in the list. Insert, position item, adds a new item to the list at a position. Pop, removes and returns the last item in the list. And pop POS, removes and returns the item at position POS. Okay, so we're going to implement the unordered list as a linked list. In order to implement an unordered list, we will construct what is commonly known as a linked list. Recall that we need to be sure that we can maintain the relative positioning of the items. However, there is no requirement that we maintain that positioning in contiguous memory. For example, consider the collection of items shown in figure 318. So that's down here. See, they're all spread out all over the place. So all we need to do then is connect them together. We're going to start off with the head, which will point to the first item. Okay, that item will point to the next one, and so on down through all of them until we get down to the end. Okay, so it's important to note that the location of the first item of the list must be explicitly specified. Once we know where the first item is, the first item can tell us where the second is, and so on. So the first thing we're going to create is what's called the node class. The basic building block for the linked list implementation is the node. Each node object must hold at least two pieces of information. First, the node must contain the list item itself. We will call this the data field. In addition, each node must hold a reference to the next node. To construct a node, you need to supply the initial data value for the node. Evaluating the assignment statement below will yield a node object containing the value 93. Okay, so we're going to go ahead and do this. Let me get Python up here. And I'm going to open up a new file. So I'm going to call this is going to be our class node. Do our init. Have self, and we're going to have our initial data. We'll pass it in. So in here then, self.data is going to be equal to the init data, and self.next, which is going to be our address to where the next one's located, is going to be none because we don't have another one right now. Okay. We're going to have a get data method. It's going to return self.data. We're going to have a get next. It's going to return self.next. We're going to have a set data. We're going to pass in new data And then so self.data will be equal to new data. And then we'll have a set next, which will pass in new next. So self.next will be equal to new next. So that's our node. So when we create this, this will create a node that will have two parts, data and next. So as we create these, we will adjust next to point to the next one, point to the next one, point to the next one as we go through here. Okay. So let's go back to the book here. I'm going to go ahead and get this saved. And oops, wrong one. And I'm going to call this, whoops, wrong place again. Go in here, there we go, week 4. And so I'm going to call this node.py. Save that. Okay, so let's go over here. So we got the node. So this is kind of showing you where this has a temporary pointer that's pointing to data, which has 93. Data has a pointer that's pointing to none, which is the way they symbolize it like this. Okay, so this is like a representation of it here. Okay, we've already put those in there. I've talked about those. Now we're going to talk about our unordered list. As we suggested above, the unordered list will be built from a collection of nodes, each linked to the next by explicit references. As long as we know where to find the first node containing the first item, each item after that can be found by successively following the next links. With this in mind, the unordered list class must maintain a reference to the first node. The following code shows the constructor. So here we have class unordered list, and then this kind of shows you how the representation of that. And then we'll have our init, which is going to be self.head equals none. So I'm going to go ahead and open up a blank off of here. So it'll be going into the same folder, and I don't have to go hunting around where I'm going to save it. So the first thing we need to do is import our node. So from node, we're going to import the uppercase node. So we're going to class unordered list, and we're going to do our constructor or our initializer, depending on how you want to call it. Don't want to pass anything in there yet. Self.head is going to be equal to none. Let's go back over here. Okay, so we could then go into another program and set up a my list equals unordered list. There wouldn't be anything we could do with it. All we'd have in there would be a pointer head that points to nothing. So the next method we're going to do is the isEmpty method. Simply checks to see if the head of the list is a reference to none. The result of the Boolean expression self.head equal none will only be true if there are no nodes in the linked list. So we'll go ahead and set this up. Oops, I'm on the wrong one. We just need self on this. And so we're going to return self.head equals none. Okay. Back over here. So now the next thing is, how do we get items into our list? We need to implement the add method. However, before we can do that, we need to address the important question of where in the linked list to place the new item. Since this list is unordered, the specific location of the new item with respect to the other items already in the list is not important. The new item can be anywhere. With that in mind, it makes sense to place the new item in the easiest location possible, which is going to be at the head. Then all we have to do is set our new node equal to what head is pointing to, and then have head point to the new node. Okay. So then this is a representation if we had a test program on there where we could add all the items into the list. So let's go ahead and do the code for this. And have add self and then pass in item. So temp is going to be equal to node item. And then we're going to do a temp dot set next self dot head. Okay, so our set next in our node, which I think I closed. No, there it is. So our set next is going to set the one we're calling to new next that we passed in, and new next on here is the item, or what's wrong one down here is head. So this is going to be pointing to the same one that head's pointing to. And then self.head is going to be equal to temp. So now head is pointing to the new one that we created, temp. So now temp is still pointing to that, but we're not going to need it anymore. It'll disappear later on in here. So, okay, let's go on to the next one. Kind of shows a representation there of how that's getting put in there. Okay, next one is the size method. All we need to do with this is be able to count these, but we can't move head. If we move head, then we lose the first one that it's pointing to. So, so in order to do this, what we're going to need is to create a pointer that's going to point to head, and then it's going to go through one at a time until it gets down to none. So here's an example of that. They're going to call it current. Current will point to head, and we move it down one more, counting each time we go through here. Okay. So let's go ahead and add this code in here. Don't need to pass anything into it. We're going to set current equal to self.head. We're going to set count equal to 0. Then we'll do a while loop while current does not equal none. We'll add 1 to our count, and we'll move current down. Current will be equal to current dot get next. Once we're done with that, we will return count. Okay. So I'm thinking we've got enough stuff here that we could do a little bit of testing on this. So I'm going to open up a new file here, and we're going to do from, and I'll have to save that other one. From unordered list, import unordered list. Okay, so we have, we can create a new list. So my list equal to unordered list. I'm going to print is list empty. My list dot is empty. I'm going to do a couple of adds here. My list dot add 93 and my list dot add 56. We're going to print added to numbers, and then my list. Well, we can't print them out because we don't have a print on that. That was my next statement in here. But we can check the size, so we'll do that. Print how many nodes, my list dot size. Okay, and then we can't do the other stuff. We can't look for anything yet, and we can't delete them out. So this is as far as we'll go with this, just to test this out. Okay, so I'm going to save this as unordered list test.py. Okay, then I got to go save this one. Unordered list.py. Okay. So let's see what happens when we run this. Okay, didn't get anything. Oh, that's because I ran the unordered list. We're going to run our test program here. There we go. No, is list empty? True, because it is empty when we started. We added two nodes. How many nodes? 2. So it's working. How about that? Okay, so let's go back over and okay. So the next thing we need to do is be able to search for a specific node. Okay, so searching for a value in a linked list. Implementation of an unordered list also uses the traversal technique. As we visit each node in the linked list, we will ask whether the data stored there matches the item we are looking for. In this case, however, we may not have to traverse traverse all the way to the end of the list. In fact, if we do get to the end of the list, that means that we didn't find the item we were looking for. Okay, so here's an example. Looking for 17. We look at 54, not it. We move down 1, 26, not it. We move down 1, 93, not it. We move down 1, 17. We found it, so now we can stop searching. So as is in the size method, the traversal is initialized to start at the head of the line of the list, as we use a Boolean variable called found to remember whether we have located the item we are searching for. Okay? So let's go ahead and put this code in. Let's see. That's my test program. There we go. Okay, so I'm going to go ahead and go down here. And this one is going to be get my notes here set up. Our search, self, and then what we're looking for. So we're going to set current equal to self.head. We're going to set found equal to false. So while current does not equal none and not found, if, whoops, where did I get up there? There you go. If current.getData equals item, then we set found equal to true. Else, we set current equal to current.getNext to move down to the next one. And then we just return found. Okay. So now we can go back to our test program and add an if statement in here. So now we can say looking for is going to be equal to, I'm going to say 56. We only have 2 nodes in there. Whoops. Okay. So now if, I'm going to do found equals mylist.search for looking for. So if found, we can print out a message. We did not find the value. Okay, so we'll run it now with looking for equal to 56. And it's going to crash because let me get rid of that so I can find this here. I didn't save this. I added that in. Okay, let's try it again. And it crashed again. Let me see what the reason is for this one. Okay, it should be item and not items when I do the over here. Here we go. So let me resave this. Run this again. So we found the value. Okay, so that worked. So we can go in here and change this to 55 and run it again. It should come back and say that it didn't find it. We did not find the value. Okay, so that all worked. Great. So we got our search done. Okay, so since 17 is in the list, the traversal process, we needed to move only to the node containing 17. Okay, so now the remove method requires 2 logical steps. First, we need to traverse the list looking for the item we want to remove. Once we find the item, recall that we assume it is present, we must remove it. The first step is very similar to search, starting with the external reference set to the head of the list. We traverse the links until we discover the item we are looking for. Since we assume that item is present, we know that the iteration will stop before current gets to none. This means that we can simply use the Boolean found in the condition. When found becomes true, current will be a reference to the node containing the item to be removed. But how do we remove it? One possibility would be to replace the value of the item with some marker that suggests that the item is no longer present. The problem with this approach is the number of nodes will no longer match the number of items. It would be much better to remove the item by removing the entire node. In order to remove the node containing the item, we need to modify the link in the previous node so that it refers to the node that comes after current. Unfortunately, there is no way to go backward in the linked list since current refers to the node ahead of the node where we would like to make the change. It is too late to make the necessary modification. Solution is this dilemma is to use 2 external references as we traverse down the linked list. Current will behave just as it did before, making the current location of the traverse. The new reference, which we will call previous, will always travel 1 node behind current. That way, when the current stops at the node to be removed, previous will be referring to the proper place in the linked list for the modification. Okay, so then the code below shows the complete removal method. You got to remember that there's a specialized part of this would be if it's the first node that we're removing, then we have to reposition head. Okay, so just to keep that in mind. So let's go ahead and pull this up. That's our test program. There we go. This is our one here. We want to put this in. Okay, so can't figure out why. There we go. So we're going to do the remove. We got self, and then the item we want to remove. So current is going to be equal to self.head. Previous is going to be equal to none. We won't have it pointing to anything yet. Found is going to be equal to false because we haven't found it yet. And then we'll do our while loop. While not found, we'll go through here. If current dot get data equals the item, then found will be equal to true. Else, previous will be equal to current, and current will be equal to current dot get next. So both of those are going to move down. And the order of this is important because we can't move current first and then set previous previous to it. It'll be off by one. Okay, so we got those two done there. So now we're going to be done with the while loop. At that point, we have found it. So if previous equals none, that means it's the first node. So self.head will be equal to current.get next. Okay. Current's pointing at the first one. That's one we get rid of. So we want to move head around it to point to the one after it. Else, previous dot set next to current dot get next. Okay, so previous is pointing to the node before the one we want to get rid of. Current is pointing to the one we want to get rid of. So we move the previous pointer around current to the one after it. And now nothing is pointing to that one. Current still is, but it won't be when we get done with the with the call. So it's clear then. Okay, so now we can save this. And we can't print anything out yet, but we can still add some more things on here. Okay, so let me get back to my test program. I got to find it here. There we go. Okay, so we got that one we added to. Still can't print yet. Did that there. So now we can do a search. Let's see, we only have the two items in there. We have the search. I'm going to change this out of here and fix this a little bit. We're going to print find 93. So let me get rid of all this here. Okay, so we're going to print okay, and then we're going to print find 100. We're going to add two more items to the list. Add 17. And we're going to add 34. can't print it out yet. Again, we'll check for the size. We'll do a remove. And we'll remove 56. And then we'll do another size. So I'll just copy and paste this one down below there. Okay. So let's run this. So there we go. It's empty when we start. We added 2 items. How many in it? 2. We found 93. 100 wasn't there. We added 2 more in there. So our nodes are 4. And then we removed 1. So now our nodes are 3. So everything worked. How about that? Okay, so now let me see if they have it in this one. What we need to do next is figure out how to print. Goes through and shows how all that works. Okay, they don't have a print in here, so we're going to add one of our own. So let me get my code up here. So we're going to add a print on here. And this is going to work like the traversal, the finding the size. The only difference is instead of finding the size or doing a search, we're just going to print out the value. So we're going to set current equal to head, while current not equal to none. So while we still have nodes in there to look at, I'm going to print current dot get data. I'm going to do end equals quote space quote, because they stay on the same line. And then current equals current dot get next. And then when we get done with the while loop, we'll just print out a blank line to clear it off and be ready for the next one. Okay, and go ahead and save this one. Pull up our test program, and then we'll put a couple of print statements in here, or places to print. So after we added 2 here, we're going to call print here, my list dot print list, and I had another print in here. There we go. Okay, so this is going to be after we added 34 here. There. Okay, so let's run this and see. Whoops. Oh. In the code here, let me go over here, where I said current equals head, it should be self.head. There. Okay. Save that. And then run this. And there we go. List is empty. We added 2 items, 56 and 93. Notice the order. We put them in as 93 and then 56, but 56 is the first one because we're adding at the head. Okay, so the last one we add is the one that's at the top. Now we have 2 nodes. We find 93 is true, find 100 is false. We added 2 more, so now we have 34, 17, 56, 93. We add 2 more numbers, and I gotta look and see what that none is there. Oh, okay, and then how many nodes? 4. And how many nodes? 3. So over here, There's where we added 2 more numbers. Okay. Yeah, okay. We got to look at this over here. Let me squish this over this way. Okay, so at 17 and 34, and then we added 2 more numbers that it did none. So it can't do this here. So what we'll have to do is cut this out of here. Okay, let's try that and see what happens. There we go, added 2 more numbers, then it printed out the numbers. Okay, so I just didn't like doing that inside the print on there. So, okay, so we got all that working. Hopefully that helps help you understand linked lists, and then we'll pick it up with the next video. Bye.